Hi! In this series, I'll be going through some basic group theory, and before we start with defining what's a group, we shall go through what are some preliminaries needed. So, firstly, we define what is known as a binary operation as a function from G cross G to G. So, it is something like your addition or multiplication, where you take two inputs from the set G and it'll be go back into G. And this operation is associative if A star bracket B star C equals to A star B holding bracket star C. So the idea is that if it's associative, then you do not need the brackets. And it is commutative if A star B equals to B star A. So the order of operation does not matter. That's the meaning of commutative. For associative, you are trying to say you don't need brackets when doing the operation. And we have our usual understanding of this operation, such as addition on the real numbers. Multiplication is a commutative operation on integers or the real numbers. But if you think about it, subtraction is not commutative because A minus B does not equals to B minus A. It's in fact anti-commutative. And minus also is not an operation on the positive integers because 2 minus 3 equals to minus 1, which lies outside the set. So you can see when something is a binary operation, so it must still be contained within the set, and when the properties of associative and commutativity hold. You can also represent your binary operation in the form of a table. So this just means 0 star 0 equals 1. 1 star 0 is 0, and so on. And suppose star is a binary operation on G and H is a subset of G. Then if H is closed under operation star, it means that the binary operation restricted to H will also be a binary operation on H. So you're saying that for all A, B in H, A star B is still in H. And then we say this is closed. And any properties from the bigger set can be passed down when restricted to the smaller set. And so with the idea of binary operations, now we define a group. So a group is having a binary operation and a set where with the certain properties. So the binary operation is associative, and there exists an element known as the identity, so that every element in your group multiplied by this identity equals to itself. So, and lastly, the last property that we have for a group is that it has an inverse for every element. And an inverse is defined to be the element where you star it with equals to the identity. One thing to note is that because you're using a binary operation, this is like the closure property in like vector spaces that you normally have. Because you already start off with a binary operation, you don't need to state that it's closed because it is in the definition of the binary operation. And we say a group is abelian or commutative if the binary operation is commutative. Also, another thing is that because the group must always have identity, groups are always non-empty, meaning the smallest group is always the one that contains the identity. Usually also we denote the identity as 1 because you can think of it as a multiplication identity or 0 for addition identity. So these are some common examples of group that I'll leave it to you to read. What to note is that Z is not a group under the multiplication because there is no inverse, even though it is a binary operation. And so we have some following properties that we want to prove is that the identity is unique, the inverse is unique, the A inverse to its inverse is still A, and generalized independence are all holding true. So these are just some very simple propositions that most of the proofs you can read in the textbook in Dummett and Foote, which is what we are using. I shall just go through maybe one or two which I've laid down over here. So maybe let's go through the first one. So how do you prove that the identity is unique? Meaning you have, let's say you have two identities, E1 and E2. So in this case, because each of them are identities, they have the property E1 cross E2 equals to E1. Because E2 is identity, so it becomes E1. But because E1 is also identity, this is E2, so E1 and E2 are equal. So you're done. And how do you prove that the inverse is unique? Well, let's just say there are two elements that leads you to becoming the identity. Then C being equals to C cross E, because E is the identity. Then this E is A cross B, so you get C equals to B in the end. And so you're done. I hope you can see how easy it is for these propositions, since this is basic group theory at the start. Along the way, it might get more challenging, but if you keep up the video, it should be fine. So the next proposition which I'll prove is known as the cancellation laws, and this applies to groups. So what you have is, if you know that AU equals to AV, then this implies that U must equals to V. And this is because A is uniquely has a unique inverse. So you can just multiply A inverse to each side and they get cancelled out. So you get U equals to V. And a consequence of this is that now you only need to show one side, AB equals to E, to find the inverse. So this means that B has an inverse. B is the inverse of A. And even though in the definition of group is AB equals to E equals to BA, so you need both sides. But you can actually just show one side once you know it's a group. Next, we can then define a group via a group table. Like, because we can define a binary operation via a table, we can similarly define a finite group using a group table, as we call it. So this group table is basically just our binary operation, but it must satisfy the properties of having inverse and identity and associativity. And you can see that this star operation has an identity because this whole column gets repeated over here. And if you just take 1, this row also gets repeated over here. So this means 1 is the identity. I mean 0 is the identity over here and over here. So in that case, what is the inverse? Well, it is what leads to 0. So 1, the inverse is 2. 2, the inverse is 1. And I hope that is clear. But the last part is it's difficult to check associativity because you don't show the associativity in the group table. But what it allows you to check is whether it has the operation has an inverse and an identity. And so some notations to take note is we'll be now using the dot like a product to simplify our notations, and x to power n just means x operated n times. Similarly for x to the power minus n is just the inverse operator n times. And x to the power 0 is always defined to be the identity of g. So I shall end off this video with doing a simple exercise for you to see. And what I'll go through is proving that if x squared equals to 1 for all x, then g must be a billion, meaning the operation is commutative. So if you take two elements in g, x times y squared equals 1 implies that xy equals to xy inverse. And we know that xy times y times x equals to xy squared times x. Then this y squared must equals 1, so it becomes x squared. Then if x squared equals 1. So we know this hence also equals 1. Meaning y times x equals to the inverse of this. And the inverse of this is xy. So y times x equals to x times y, like here. Hence, g is a billion. So you can see how improving group theory, we always start out with the definitions and we work our way to the result and conclusion that we want. So with more practice, you'll get the hang of it. And do try it out for exercise 25, 26 and 27, which gives you an idea on how to prove subgroups and what is known as cyclic groups, which we'll be going through in the subsequent videos. That's all for this video, and I hope you have enjoyed it. Feel free to like, share and subscribe, and leave any of our comments down below. Thanks.